guys, welcome to another chemical engineering tutorial brought to you by the ChemEng student. In this lesson we're going to take a look at steady state heat transfer operations. Now this is the final video for our annual competition whereby you can win £1,000 every month for an entire year. So make sure to check out the question at the end of this video. So in this tutorial what we're going to look at is the following aspects of heat transfer. We're going to take a quick recap on the basic operations for heat transfer. Then we'll take a look at the thermal resistances and then how we construct resistance networks, and then we'll put it all together and we'll look at a working example. Now all the work that is done here is using the fundamentals of thermofluid sciences citation. So if you want to follow along or you want more information, then this is the source of all this information. So the first thing that we'll take a look at is the basic heat transfer operations. And in simple terms, the driving force for heat transfer is a temperature difference, i.e. the greater the temperature difference, the increased rate of heat transfer. Now if we consider the following schematic, then what we can do is we can create what's called a general energy balance. And this will allow us to illustrate the movement of the heat. So if we take this slab, then we can see here that we have different temperatures on the left. So at the left hand side is 20 degrees, and on the right we can see that it is now only 3 degrees. So our range or our direction of heat is going from left to right, and that's denoted by Q. Now what we can say here is we can say that Q in, now this dot represents flow. So if you see things with a dot, it simply means that this is a flow rate of heat. So it's the amount of heat coming in minus the amount of heat that leaves, and that must be equal to the differential equation of the energy of the wall, so that's E wall, with respect to T. So T would be the thickness of the wall, or you can have it as with respect to time. It depends on what you're wanting to validate your results. Now what we are going to say here is because there is no generation of heat, and that refers to the DE wall section, or we have heat retention within the wall, then what we can basically say is this term would basically disappear. We would bring the minus Q out across. So what we have to say here is that for steady state heat transfer operations with no generation or retention, Q in must be equal to Q out, i.e. the amount of heat that comes in must be equal to the amount of heat that leaves. Now if we bring this to Fourier's law, then this is for heat conduction. And since heat transfer through the wall, because it's solid material, is done by conduction, then what we can say here is that Q wall conduction must be equal to minus K A dt by dx. Now, if you're familiar with Fourier's law, then chances are, if you've done heat transfer, chances are you've heard of Fourier's law. Now, Fourier's law is basically the fundamental law and rules to express the mode of heat transfer. So the K here is the thermal conductivity of the material, i.e. how well does this material conduct heat. So for example, metal will have a higher thermal conductivity for heat compared to, say, wood. Now A is the heat transfer area. So that would be like the surface area of this shape. Now dt is the change in temperature with respect to the change in x, so the direction of x. Now if we do this per unit length, i.e. if we take it as like for 1 meter, then we can actually create a differential equation. Because what we can say here is that L will be the length or the thickness of the material. Therefore, if we bring the dx, which is here, across to the other side, and we then say that the Q wall conduction, so the energy for conduction through the wall, with limits of 0 to L, i.e. the thickness, must be equal to minus, because that's this minus here, of the integral between the initial temperature, so that's T1 here, and the final temperature, T2, where it's Ka dt. So that's us started to derive the heat transfer operation per unit length using Fourier's law for conduction. Now, therefore, if we integrate with our respective limits, then obviously the 0 would cancel itself out. So what we can do here is now express the conduction for heat transfer through a solid wall is equal to Ka. Now it's T1 minus T2. You can also express that as delta T divided by L, because this L, when you perform the integration, you would just divide by L. Now, if we stick with the idea of heat transfer through the plane wall, then what we can do is we can now express thermal resistances. Now, a thermal resistance is basically what it says on the tin. It's basically how much resistance does this material have to hold back the rate of heat transfer. Now, the resistance for a solid plane wall is going to be L divided by Ka, i.e. the thickness of the material divided by the thermal conductivity of the material multiplied by the heat transfer area. Because ultimately the resistance is going to be the inverse of the thermal conductivity. Because thermal conductivity is a measure of how well it will allow heat transfer to take place. So the inverse of that must be the resistance. And the reason we have L and we have A is we have to take account of the geometry and the size of the material. Therefore, we can actually express, because we had Ka over L in the previous equation, so we could actually replace that with R, so that would be the resistance, and we can actually get an expression for rate of heat transfer as a function of the thermal resistance. So this time it would be delta T over the thermal resistance at the wall. So we've now derived two equations based on Fourier's law for conduction. Now the question would be, this is for conduction. Now, what do you think the resistance would be for convection? Because conduction, we deal with solid material, i.e. we have the length of the material and the cross-sectional area of the material. So if we look at convection, then what we have is we need to account for H, which is the heat transfer coefficient of the material. We have the surface area, we have the surface temperature, and then we have the infinite temperature. So that would be the infinite temperature of the fluid. Now, therefore, what we can say is that the resistance for convection must be 1 over the heat transfer coefficient for the fluid multiplied by the heat transfer area. It has to be the inverse. It's inversely proportional. Now, a graphical way that we sometimes, or most often, use to express thermal resistances would be things like this. So the way that we would read this is we have our infinite temperature T1. So that would be, say, the temperature of the fluid at the left-hand side. We would have a resistance, so that's what these diagonal lines are. So that tells us we have a thermal resistance and its convection from the infinite temperature to the surface temperature, T1. Then we have the thermal resistance for conduction, that's our wall. Then we'll have the surface temperature of the plate, which is at T2. And then we'll have the convection resistance from the plate to the infinite temperature of the fluid on the right-hand side. So that's how you would read these types of graphical representations. Now, one thing to note is that radiative heat loss this is an advanced heat transfer module. However, here what we're just going to do is we're just going to highlight and showcase the equations that govern the radiative effect. If you would like to see more on radiative heat transfer in more advanced detail, then I'll put a link in the description to our highly popular heat transfer course, and you can check that one out if that is something that you're interested in. Now, when we talk about radiative heat transfer, we need to consider two new parameters, because regardless of whether we have convection or conduction, everything will have radiative heat transfer effects. And the two things that we need to consider here is the emissivity, given by E, and the Stefan-Boltzmann constant, given by alpha. Now, this constant is 5.67 times 10 to the minus 8. And what we can do here is, for a resistance for radiative heat transfer, we have, it's basically exactly the same as the convection, but rather than it just being H, it's the radiative effect for the heat transfer coefficient. But this is a function of the emissivity and the Stefan-Boltzmann constant. So what we can see here is, rather than just having H rad or H radiation is actually the emissivity multiplied by the Stefan-Boltzmann constant. And therefore, if you wanted, you could replace that with these two parameters as well. But notice, in every case, you have to take account of the geometry of the system that you're working with, i.e. A, in all cases. Now, if we take everything that we've seen so far and we put this into what's called a thermal resistance network diagram, sometimes denoted as TRN, then this is basically a very convenient way of representing the resistances to heat transfer. Now, we can see again, we have, this is basically your thermal resistance network. We kind of already discussed it, but now we'll see it using the geometry of the system as well. So what you can see here is your heat transfer is going from left to right. Now, this is a single layer, so we only have one means of solid conduction resistance. So we have our infinite temperature, T infinity 1. We have our convection resistance, so that's from that point to the plate surface. We will then have the surface, the plate itself, resistance, that's your conduction, and that's represented here. And then you have your surface temperature T2, and then we have our second convection resistance to the infinite temperature T infinite 2. Now, notice a key distinction between the convection resistance and the conduction resistance. You can see that in the cases that the conduction resistance is significantly higher than that of convection, because solids have a greater resistance to withholding heat compared to our counterpart, which is the convection. Now, if you were to look at this in a double layer system, then the beginning and the end is exactly the same. And this time we're including the resistance formulas. So from T1, T infinite 1 to the surface temperature T1, it's the same thing. Then from T1 to T2, we have our first wall conduction resistance. Now, this phenomenon here is a contact resistance point. Now, that is out with the scope of this tutorial, but again, we cover that in significant detail in our heat transfer course. But this has its own properties in thermodynamics and heat transfer. So again, I'll put a link in the description if you are interested in that. But then from T2 to T3 this time, it's just another conduction resistance. So this time it would be the values of K2 and L2, and then finally we round off with the second convection heat transfer resistance. Now, if we consider what the overall resistance equation would actually be for the double layer example, because ultimately sometimes it can be a bit of a pain to write all of these individually. So what we can do is actually combine these to see what the overall resistance would be from this point to that point. Now, we already see here that we have 2 parts for convection and 2 parts for conduction. Therefore, our total resistance would be R convection 1 plus R conduction 1 and so forth. Now, what we can then do here is we can simply substitute in all of these values and pop them into this equation. Ultimately as well, if your areas here were constant, you could take A out as a constant here, or common factor between the conductions, but you couldn't do that in terms of the convections. So you'd have to be very, very careful. Now let's take a look at a working example here. We'll put it all together and we'll see how we actually solve this system. So what we want to do is we want to determine the rate of a steady state heat transfer through this piece of glass. As per the details in the diagram, we have a height of 0.8 meters, we have a width of 1.5 meters, and we have thermal conductivity of 0.78 watts per meter degrees Celsius. Now we have our H values, H1 and H2, we have our thickness, we have our starting temperature, which is 20 degrees, and our final temperature, which is minus 10 degrees. So what we can then say is the total resistance of the system is going to be the first convection plus the conduction resistance of the glass, and then the second convection, which is on the right hand side of the glass plane. Now from here, we simply need to populate the formulas that we have on the respective data from the diagram. So from here, what we can then say is that we have number 1 for convection, we have 1 over H1A. We know that H1 is 10 watts per meter squared degrees. And we know A will be 1.2. So that will give us a resistance for convection 1 at 0.08333. And you can see that it's degrees per watt. So for every watt of energy, we lose and resist 0.08333 degrees. So not a huge amount. And then for the glass, same thing as before. And then for convection number 2, exactly the same thing as before. Now here, this should actually be 40, not 10. All right, so just pop that in there as 40. Then all we need to do is add all these together, and that gives us our total resistance. Now from here, we need to bring in the original steady state heat transfer equation, which was given by T infinite 1 minus T infinite 2, so that's the total temperature difference, divided by the total resistance. Therefore, our total temperature difference will be 30 degrees divided by R total, which tells us that this system, the steady state heat transfer for this, would be 266 watts. And that's how you would go about applying these fairly simple systems and equations to steady state heat transfer problems. So now it's your final chance to win £1,000 every month for an entire year. And all you have to do is answer the following question correctly. What does the emissivity represent in the context of radiative heat transfer? So in order to qualify, you have to comment your answer to this video, like and subscribe to the channel, and make sure that you're subscribed to the Facebook page, because that's where we will release the name of the winner on the 5th of next month. Entries end on the 30th of this month, so make sure you put your answer by then. And this is the final month for these competitions, so make sure your entries are in. So that's the end of this lesson. Thanks for watching. Hopefully this was helpful in understanding the concept of steady state heat transfer. If you liked this video, please like and subscribe to the channel. It really helps us reach as many chemical engineering students as possible. Thank you for your time, and we hope to see you in another video.